All right, good morning, you guys. It is Tuesday, April 21st, and we are kind of getting down to the wire here. It's getting towards crunch time. We're down to, I'm not sure, I'm pretty sure you guys are probably somewhat keeping track. You guys have 24 school days left before your graduation day. I know it's not at all what you guys had in mind for finishing out your senior year, but hang in there, keep your head up. It is what it is. When you guys look back eventually, it'll just be kind of a defining moment in your life and something you guys will never forget. So just keep your head in the game, finish strong, and make the best of the situation. Okay, guys? So with that being said, with 24 more school days essentially, that means that we're down to basically our final 12 assignments. We're going to get into some of the nitty gritty, some pretty decent stuff here, some stuff that'll, again, hopefully help you better prepare yourselves for that next chapter, okay? So what we're going to do today is we're going to continue on with section 6, but we're going to get into the graphing part of it, okay? So we're going to try and take this piece by piece, and I'm going to try and really explain it well without over talking. And taking things or making things take too long. So essentially what we're doing is we're graphing today, okay? We're going to graph some fairly familiar looking polynomial equations and stuff like that. But what we're going to do is we're going to be very precise. We're going to implement or put in all of the different tools that we have in our repertoire at this point, going all the way back to what we learned in basically Algebra 1. So what you can see here, the directions, and I put these out of order inadvertently. The directions today are going to tell you to use 3 different things, okay? But in reality, it's more like 4 or 5 different things. It's going to say use intercepts. That's literally the x and y intercepts of a graph as potential points that we can use to help make our graph as precise as possible. So we're going to talk about intercepts. We're going to remind ourselves of what this section has kind of been building toward, which are our asymptotes. But then we're also going to look at the first and second derivative test, the extreme points, the maximums, the minimums, and the points of inflection, okay? So we're going to start with relatively simple today, okay? We're going to go back, like I said, all the way to Algebra 1 essentially, and we're going to talk about how do you find the x and y intercept, okay? So for our intercepts, it's super simple. The intercepts are the 2 specific points, or in some instances, the multiple points where a point crosses the x-axis or the y-axis. If we just think very directly about this, when a point is on the x-axis, meaning when you're finding the x-intercept, you're finding a point along here, and any point on here has a y-coordinate of 0. And then vice versa, when you're talking about the y-intercept, a point where a line crosses the y-axis, any point on the y-axis, whether it's up or down, has an x-coordinate of 0. All we do to find those specific points is direct substitution. So like in this instance right here, this is the obvious one. When you plug in 0 for x, when you're finding your y-intercept, that's the point where the x-coordinate is 0, you're literally plugging in 0 for every x and seeing what you get for y. So you're just doing direct substitution into the original function, but you're plugging in a 0. When you plug in 0 for all those x's, you get y equals 2. So when x is 0, y is 2, that means the point 0, 2 right there. And again, that's my y-intercept. That's the point on the y-axis, but it's there because the x-coordinate is 0. Now, the same is true for the x-intercept. The x-intercept is when you plug in 0 for y. The thing I want you guys to see here is this. When you plug in 0 for y, you obviously get 0 equals all of this still. And then you have to actually solve for x. But what you're going to notice is this. To try and solve this cubic polynomial, like if you try and group these first 2 terms and group those last 2 terms, you're not going to be able to do factoring by grouping. Literally to plug in 0 and solve for this would mean trying to do, you'd basically have to do synthetic division to try and get to what x's solutions would be. So what we don't want to do today is we don't want to kill ourselves to find intercepts. These are going to be the relatively small ones. So what we're going to do is we're just going to say not easily solvable. And this is really only for x and y intercepts that we're gonna go that route, okay? If you can't easily solve for the x-intercept when you plug in 0 for y, then like I said, don't kill yourself for it. We'll be able to find enough other points to probably graph this relatively accurately. So that's how we find our intercepts. You plug in 0 for x and y and solve for the contrasting coordinate, okay? All right, asymptotes. We're gonna solve for our asymptotes in partial way, the way we've been doing things the last couple days, okay? For vertical asymptotes, vertical asymptotes are any x value that's going to make the function undefined. So what I want you to think about is this: is there any number that I can plug in for x's up here? And you're going to wrinkle your eyebrows a little bit at this if you really think about it. Is there an x value that I can plug in so that when I try and do all the adding and subtracting and exponents, my calculator is going to kick back a domain error? And the answer to that is no. There's no x value that's off limits for a polynomial, which is what tells us that there is none. There is no vertical asymptote in this function because there's no x value that's going to give you a domain restriction, okay? Now, horizontal asymptotes. This is the part that we've been working with for the last couple days with these infinite limits, okay? You find horizontal asymptotes by taking any term that's in a fractional function, a rational function. You put it over the largest degree of x and you plug in infinity for any remaining x's. It's what we've done the last 2 days. What you did yesterday to finish up your assignment and what you were working on last Friday with those infinite limits. The thing I want you to see here is this. By the very description that I just gave you, a horizontal asymptote is what you get when you do the infinite limit test on a fraction. Tells us that the only types of functions that actually have vertical asymptotes, other than trig functions, are fractional functions. This isn't even a fractional function, so that tells us there aren't any. There's no vertical asymptotes in this one, okay? Now I know this is going to be a little bit weird because this particular problem has no vertical or horizontal asymptotes, and the problems that I'm going to give you guys today for your assignment, most of them do have those. So we'll go do a second example before we call it quits here and what that's going to look like, okay? But right now, here's what I want you to see. The first thing you're going to do today is you're going to find your x and y intercepts if they're easy to find. Then you're going to find your asymptotes. Neither one of these existed for this polynomial function. They will on example number 2, okay? The next thing we're going to do is we're going to find our extrema. We're going to use the first derivative test to find any maximums or minimums, and we're going to use the second derivative test to find any points of inflection. So this is where we differentiate. What is the derivative of our original polynomial? It's 3x squared minus 12x plus 9. Set that equal to 0 and solve for any x values of any extremes. So this is obviously all three of those terms are divisible by 3. When you factor out a 3, you get x squared minus 4x plus 3 equals 0. You can basically divide this 3 to the other side. It goes away. And then you can factor this polynomial to solve for your critical x values. What is this factored? It's x minus 1 and x minus 3. What does that mean your critical values are? My critical values are 1 and 3. Those are my critical numbers, right? But if I take them, 1 and 3, and plug them back into my original function, I will get their corresponding y values and the locations of some more points here. So when you plug in 1, you get 1 minus 6 is negative 5, plus 9 is 4, plus 2 is 6. 1, 6. So if I'm graphing here, over 1, up 6 is right there. And then if I plug 3 back in, 3 cubed is 27, 3 squared is 9, 9 times 6 is, 9 times negative 6 is negative 54, 27 minus 54 is negative 27, but then plus another 27 gets me right back to 0. 0 plus 2 is 2. So I get the point 3, 2. That's over 3 up 2. If we just put this little portion of the graph together, here's what we discover. This must be a maximum right there. and this must be a relative minimum right there, okay? Let's do our second derivative test. The second derivative is just the derivative of the first. This will give us any points of inflection, okay? But let me just kind of reiterate what I know right now. I know that this is a maximum up here at 1, 6, and I know that this is a minimum right there. I didn't draw it particularly well, but hopefully you can kind of see it. These 2 points have to be maximums or minimums because they're the critical points of the first derivative. Second derivative is 6x minus 12. Set that equal to 0. Solve for any x values of any critical numbers. Okay, factor out a 6, divide it away. So here's 6. You get x minus 2 equals 0. Divide it, you get x minus 2 equals 0. So obviously the critical value there is 2. If you plug that back into your original polynomial, 2 cubed is 8, minus 2 squared is 4. 4 times negative 6 is negative 24. 8 minus 24 is negative 16. Negative 16 plus 18 is 2. 2 plus 2 is 4. 2, 4 is a point of inflection. Over 2, up 4. So I didn't really do a great job. Luckily for you guys, I stole some whiteout from school. All right, there it is. This is a point of inflection for my graph. So it's the point where a frowny face turns into a smiley face. And basically, here's what we have. These two were extremes. One was a max, one was a min. This is a point of inflection. It's the point where the curvature of the graph changes. The fact that this is the only point where the curve changes means that this smiley face never stops again. It keeps going like that forever and ever. And same thing over here. This frowny face goes through right there, but never stops being a frowny face. Now, obviously, with this one, we kind of were clued in on to that at the beginning because we all know that a cubic function is an S-shaped curve. So cubic has 2 extremes. But again, we were able to kind of splice this together with a whole bunch of different things to get a pretty accurate looking graph, even though we didn't have to do a whole lot of like plugging in random points. We didn't plug in any random points. We plugged in critical points, okay? So this is what you're doing today. You're finding intercept points, you're finding asymptote lines, and you're finding critical points, and you're basically blending them all together to get the different, or to get as accurate looking graph as possible. Okay, this is really a better example or a better instance of what your assignment's going to look like. You're going to have a lot of fractional equations today, okay guys? A lot of fractions, rational stuff. Okay. Let's talk again, very specific in terms of steps. To find the intercepts first, you plug in 0 for x and you solve for y. And then vice versa, you plug in 0 for y and solve for x. So when you plug in 0 for x, here's what you get. Y equals 0 plus 1 over 0 minus 1. So you get y equals 1 over negative 1. Your y value is negative 1. So what is that? That's my y-intercept. 0, negative 1 is right down here. And I'm going to make my points kind of big so that they hopefully stand out and you can see them. There's my y-intercept. My x-intercept is when we plug in... sorry about that. Like I was saying, your x-intercept is when you plug in 0 for y and you solve for x. So this one actually seems like it might be kind of confusing, but it's not at all. When you plug in 0 for y, you get 0 equals x plus 1 over x minus 1. If you just multiply this x minus 1, it goes over the other side, but the 0 wipes it out. So it's 0 equals x plus 1, subtract 1, you get x equals negative 1. So I get the point negative 1, 0. That's right here. So they're really close together, but if you look at those are just 2 random points on my graph, but we get them fairly easily by doing Algebra 1 material. We get them by just finding the x and y intercept. Okay, asymptotes next. Vertical asymptotes really don't require any like computation. Vertical asymptotes are lines that are vertical, so they start with the letter x, and they are the x values that prevent the original function from being defined. Okay, so they are points along the domain where the function itself is not defined. If you look, the function is a fraction now. The only time a fraction is not defined is when the denominator is 0. So if you look, what x value makes the denominator 0? It would obviously be 1. 1 minus 1 is 0. So the value x equals 1 is an off-limits x value because it can't go back into your original function. What does that tell you about the graph at that point? It tells you that it's not defined. It is a vertical asymptote. So there is a vertical asymptote for this graph at x equals 1. Horizontal asymptotes are the ones we have to work for. Horizontal asymptotes are when we have to apply the infinite limit. The limit as x goes to infinity of the function. So how do we find the limit as x goes to infinity of this function? We do the infinite limit test. We put every part over the largest x. So this becomes x over x plus 1 over x on top, and then x over x minus 1 over x. The top, these x's cancel, but you have to have their coefficient of 1. So it's 1 plus 1 over, and I'm going to do my substitution, 1 over infinity. And then the bottom is the same thing, 1 minus 1 over infinity. So if we stop and think about this, this is 1 plus 0, because 1 over infinity is equivalent to 0. 1 over infinity down here is equivalent to 0. It doesn't matter if you're adding or subtracting 0, this still just becomes 1 over 1 or 1. What we have to recognize is that is the horizontal asymptote y equals 1. So not only is there a vertical asymptote at x equals 1, there is a horizontal asymptote right there. Okay, so we have vertical and horizontal asymptotes. Now, those two didn't exist in that first example that I gave you guys, right? There were no vertical or horizontal asymptotes. This time there are. What the first example had that was nice was it had first and second derivative extremes, okay? Here it's going to be a little bit different. So what you're going to see is we're not going to get a lot of help from here to the end, okay? If we look at our first derivative test, the first derivative, obviously, we would have to use the quotient rule. It's x plus 1 over x minus 1. So it's the bottom times the derivative of the top, so x minus 1 times 1, minus the top, which is x plus 1, times the derivative of the bottom, which is 1, all over the original bottom squared, so x minus 1 squared. Okay, I'll just kind of hammer this out real quick. When you distribute up here and combine like terms, you get 1x minus 1x, so the x goes. You're left with negative 1 minus 1, which is negative 2 over x minus 1 squared. Now, we get a critical number here. Our critical number is x equals 1, okay? But here's the thing. Even though the first derivative says that 1 is an important number or a critical number, we already know that it's actually not. It is a critical number, but it doesn't give us an extreme. X equals 1 is the location of our asymptote. So even though we get a critical number here, it doesn't help us because it's just simply the location of the asymptote. So that's our only critical number here, and it doesn't actually give us a point. It doesn't give us a maximum or a minimum. So here's what this tells us. There's no first derivative extremes. There's no maximums, so there's no high points in the graph, and there's no low points in the graph. They're just infinite points in the graph. There's no point where it stops going up, starts going down, or vice versa. The second derivative is going to kind of be more of the same. If we think about this, I could just, since I got rid of my x's on top, I could move this x minus 1 up with it and just do chain rule to find the second derivative. What's negative 2 times negative 2? It's negative 4. X minus 1, drop down the exponent, times that by the derivative of the inside. But here's all you get here, negative 4 over x minus 1 cubed. What's again the only critical number? X equals 1. Okay, in this instance, this is where the first example was better than the second example, okay? We don't get any critical points here. We don't actually get any points of inflection, so there's no points where the curvature changes, and there's no points that are maximums or minimums, and yet there's these 2 points right in here, and there's asymptotes. That basically tells us the only way to connect those 2 points and approach both of these asymptotes, for lack of a better word, is with a frowny face. So if you think about it, nowhere does that curvature change. It continues infinitely in both directions, and there's no actual topping out point where it starts going back down, so there's no first derivative or second derivative change. What ends up happening here is we're really not going to know what it looks like unless we plot some points. So if we just pick some arbitrary points to the right of this, like if you pick the point 2, because 2 is to the right of that, plug it in, you get 2 plus 1 is 3 over 2 minus 1 is 1. So you have the point 2, 3. That's over 2 up 3. And then basically what that tells us is the other portion of this curve is up in this area right here. Even if we don't pick another point, we know that this is going to be a concave up or a smiley face part of the curve, and it's got to approach the asymptotes. That's what graphs with asymptotes do. They approach them. So it's just this two-part curve. The unfortunate part is we had to get this point the old school way. We had to just guess and check. We picked 2 because 2 was to the right of our 1 in our domain, but we just got a point up here and we just figured that it had to be a curve like that. Most of your homework problems you're going to get more points to work with. You're going to get intercepts, and you're going to get points that are extremes, maximums and minimums, and points of inflection that'll help make graphing easier. Okay? But ultimately, this is the design. You do intercepts first, asymptotes second, and extrema last. Maximums, minimums, and points of inflection. So if you have questions, ask them, okay? If we need to spend tomorrow going back through this basically, like if I get a bunch of responses that say, hey, I have no idea how to do any of these, then maybe I'll just pick 1 or 2 of them and maybe a different example to go through. But do what you can and let me know what kind of questions you're running into. Okay, guys, have a great Tuesday, and we'll talk to you later.